Okay, now we are going to start. Yesterday we have seen some of the provisions, some of the pictures, and how you can have the earthquake resistant measures. So today we'll have the lecture on the Codal provisions. The much need to be done by you. So I'm here to just facilitate you that how you can make your structure earthquake resistant by the Codal provisions. But what are the provisions which are given in the codes? So in the codes, we are in any type of building, we are having two forces, mainly basically two forces acting on the building. One is wind force, another is earthquake force, and another loads are like live load, dead load, snow load, but most dangerous load is earthquake kind of a forces. Why? Because in case of wind force is applied on the exposed surface area, and you know it is applied in a particular direction, and its reversal moment is after a very long time. The moment of the wind is reversed after a very long time, and it is a force type of loading. The force type of loading is applied due to the wind force. But in case of earthquake loading is a random type of motion, which is random type of ground motion, and its reversal effect is in time based, and in a very short time the force used to be reversed also. So it is a very dangerous kind of a movement of a building. It will shake your building, and the loading is the type of loading is a displacement type of loading, because your building is displaced from the bottom. So it need to be the earthquake load need to be resisted by the building, and the earthquake forces used to you can have different mode shapes of your building during earthquake, like compressive force, tensile force, shear force, and twisting moment can be there in case of buildings. Now, what are the design principles? What are the design principles for the earthquake resistant buildings? First principle, that design building to behave elastically during the earthquake. Because if your building is in elastic state, what is the elastic state means? That if your building deform, it will come back to its original position if it will remain in elastic state. But another thing is that you need to design your building to be remain in the elastic state. How? By allowing some local damages to the buildings. So the second approach is the approach which the structure engineer used to follow. That they design the building in such a way that it will have small damage, and the energy is released due to those damages. In case of when we used to design the building a particular, we need to take care that the building should have a minimum stiffness so that during the minor earthquakes no damage occur in the buildings, and during the moderate shaking small damages may occur during the building, and during the when we are having a severe earthquake shaking. In severe earthquake shaking, we need to have some we will have some structural damages, but not collapse. Building should not collapse. So that is how we always used to say that we are designing the earthquake safe building, not earthquake proof building, earthquake resistant buildings. Why? We are allowing some of the cracks, some of the damages in the buildings. Now, if we need to design the earthquake proof building, it is not there that we cannot design, but the cost of the building will increase many times. As you have seen that many nuclear power plants and many other important structures, some other kind of provision is there, like base isolation technique is there. We are providing dampers in that buildings. What do you mean by damping? Dampers means they are damping the earthquake forces, because that means they are resisting the movement of earthquake forces. They are resisting the movement of a building because of that damping effect. Like in your cars, you are having shock absorbers. Like that, the building, if you will connect your building with those dampers, it will behave like a shock absorbing equipments, and your building will be safe during the earthquakes. Now, to improve the ductility of the structure, if what is the ductility of the structure? That at a particular displacement, if you are applying the displacement of a building, the building will not having will not having any damage or any cracks. That is called as ductility of building. That is the allowance of the building. We need to allow the building to move at a particular displacement. That's why whenever we used to do some of the experiments in the earthquake model, we used to do that displacement type of loading in that particular structure, like push and pull kind of a behavior, cyclic type of a loading, and large displacement and without collapse and non-reduction of the strength. At the same time, the structure should not collapse and the strength of the structure should not reduce. Building need to be designed to resist the relative displacement induced at its base. Another design principle is the large displacement which is induced by the earthquake at its base. The building need to resist those displacement. That force we are calling it as the base shear force. Base shear force, if you will see your IS code 1893, if you'll see the code 1893, you can see that base isolation, base shear. Just open that code. (1893) Part 1. Here in this 1893, this seismic zoning map of the country is giving. Here you can see the seismic zonation map. Here you can see the seismic zonation map in which 4 zones are there. And here some of the terminology for the earthquake engineering is given, like what is the damping, what is the damping effect, the effect of internal friction, imperfect elasticity of the material, slipping, sliding, etc., in reducing the amplitude of the vibration. That is called as damping. Like here it is given design based earthquake. What is the design based earthquake? It is the earthquake which can responsible to accepted to occurs at least one during the design life of the structure. Like I told you earlier also that its return period is around after 500 years. And in case of maximum considered earthquake, the return time is around 2500 years that it will return back to the structure. But the probability of maximum considered earthquake is only 2%, that the forces beyond the maximum considered earthquake will come during if the earthquake will hit in any region. So here all the terminology is given. You can read it from your code. So here the vertical distribution VB is given AH multiplied by W. So in the later slide, I will tell you how to calculate this base shear. Then there are 4 aspects of the buildings for which building need to be designed. First is seismic structural configuration. first aspect you need to design your building is your configuration of that building. Configuration of that building and shape of the building, matters a lot during the earthquake resistant design of a building. Earthquake resistant in your code, in your codal provision, if you will see that where is that configuration, the table is given here. On this page, like irregular and irregular configuration of the building. So here you are having one question: list of failure mode of your building, safety measure of your building subject to earthquake. So you need to read this code and answer your question. Here are the various irregularities, like torsion irregularities. Torsion, if you will have X shape of structures, L shape of structures, or other non-irregular shape of a structure, so torsion effect will be there. It can be understood by the very simple example. If you have done some of the physics experiments in case of your +1 and +2, we are having concave and convex lenses. Concave and convex lenses. If you will have concave lenses, the light passes through the concave lenses, and you will see the point inside the mirror. But in case of convex lenses, the load transfer, the light transfer is the outside your lens, and you can see that that light outside the lens. In the similar manner, this irregularities, that the irregular configuration you can observe, and if the eccentricity is lies outside your building configuration, then torsion effect will be there. And another is re-entrant corners. Plan configuration of the structure and its lateral force resisting system contains re-entrant corners, where both projection of the structures beyond the re-entrant corners are greater than 15% of its planned dimension, and it is in the given direction. Here you can see the re-entrant corners. Here you can see the re-entrant corners. These are the re-entrant corners. Your building will fail if you will plot the deflected shape of these kind of structure. The re-entrant corner. These are the re-entrant corner effect. Another thing, diaphragm discontinuity. Diaphragm discontinuity means here in the IS code you can see diaphragm discontinuity. Suppose you are having opening in your building, you are having any duct, you are having any anything which is which is there in your diaphragm, means this is diaphragm discontinuity. Continuity means if you are having simple rectangular building, and simple rectangular building, if you will calculate the moment of inertia, and whenever you calculate the moment of inertia, it lies in your rectangular and square building. But if you are having the discontinuous diaphragm, your moment of inertia and moment of resistivity will differ, and building will behave in a different manner in case of earthquake, and it will fail. Another thing here is out of plane effect, out of plane offset of the building. In here you can see that out of plane behavior of the building is shown. Like this, if you are having rectangular kind of a structure, it is very strong in this case, because you are having in plane kind of a forces, but in other direction it is very weak. That is called as out of plane movement of the force. I have explained you earlier what is in plane and out of plane behavior of the structure. Now another is here, non-parallel system. Non-parallel system is also given in this IS code. This is the non-parallel system. If you have you are having an octagonal shape, if you want to resist your building, you should have the shear walls at a different interval of time, so that whenever the earthquake force came into picture, basically walls used to fail in shear. So you need to have the shear walls at a different interval of time, different interval of places in your structure. Another definition of irregular buildings: vertical irregularities like stiffness irregularities or soft story. What is the soft story? If you are having the parking space below your structure, if you are having parking space below your structure, then it will be act as soft story. What is this soft story? I'll tell you by this picture. So this you can see here, when the structure is having soft story here, if there are many factors affecting that multi-story building. First factor, if you are not, this is the bare frame, if you will calculate the moments, see, whenever the earthquake force is there, plastic hinges used to form in at every junction point of a structure, and the structure used to behave in a similar manner. All the joints will move in a similar way in case of bare frame. But if you are having infills in between, in our case in India, we are having infill walls. Whenever we used to construct any RCC frames, infill walls are there. When you will construct that infill walls, we thought that these are the not load bearing walls. But in case of earthquake, these infill walls act on the column, because you know these infill walls induced additional shear force, additional pressure on the column, and you need to design those column for those pressures also those shear pressures also, because of this because of these infills. So infill, if you are having infill kind of a building, lot of research is going on for infills. I am also doing one research by this infill walls. In another lecture, I will tell you that whatever I have made my technology for load bearing type of structure, now we are testing that technology in the frame structure also, that how it will behave as a infill. If it is because in that technology I have increased the elastic property of a building by introducing this viscoelastic link elements. Those link elements allows that buildings to deflect more and come back to its original position, and we are testing it whether what effect it will create on the column, if that building will affect less on the impose less shear force on that column. That our purpose is solved and our technology is successful. Now in the third picture, if you will see that if upper floors are having infills, but lower ground story is not having any infill walls or any shear wall. So in this case, you know, all the forces will be concentrated at the lower portion of the structure. In here, all the forces will be concentrated, and you know, you will have the additional moment of earthquake forces in this region. And in this region, as in case of picture 1, like the plastic hinges is formed at every junction, every corner of the point. But in case of soft story, the plastic hinge will form in this region, and you know, this region will behave in different manner as compared to the upper one, so that the breakage of column will be there at the junction point, and this story will be collapsed. How we can save that soft story effect? You need to provide shear walls at different interval of time, different interval of places, so that that building can be saved during the earthquake when it induces the shear forces. Another thing, as I have shown you the stiffness, how the stiffness irregularities there. A soft story is one of in which the lateral stiffness is less than 70% of that in the story above, or less than 80% of the average lateral force of the 3-story above. See here the stiffness. What I have told you, that if the building is having ductile kind of a behavior, then the building will behave well in during earthquake. But in case of soft story, the 80%, when the load is distributed among the each story of your building, but the 70%, the upper stories, the stiffness the stiffness of whole the story up to suppose 100% stiffness there, 80% stiffness will be concentrated on the lower part of the structure, only on the lower part of the structure where you are having the soft story effect. So here you are having certain irregularities. Another thing is mass irregularity. Mass, like I have told you that in case of when you are having large water tanks, if you are having swimming pools on your top of your building, so this is called as mass irregularities. If more mass is there, the inertia force is proportional to mass of the building. Another thing which I will tell you, that the building is having its natural time period. Natural time period means that the time period in which the building will not oscillate. In that natural time period, the building is having the natural frequency also. Natural frequency means every buildings have natural frequency. Like I'll tell you about this later. First, the main challenge is the building should be able to withstand the damage under a small intensity of shaking and with no collapse under the high intensity of shaking. Now, another thing, these are the basic design principles. So, first of all, we need to design the slab. Then we need to design the beam for flexure as well as shear. Then we use to design the columns and structural walls to be stronger than the connecting beams. Design the beam to the column, beam to the wall, and slab to the wall joint. Design the foundation of the slab. Ensure that the soil beneath is capable of resisting the loads and above under the loads from the above under the strong shaking. So this is the principle. Now how you can design for the earthquake resistant features. First of all, prepare the improved structure analysis model for the building. Estimated the fundamental time period, natural time period. If you will see your code here, that time period, fundamental time period or natural time period is given here. This is the fundamental time period, clause 7.6. Here you can see here fundamental time period is given for RCC frame building, for steel structures, as well as for brick masonry structures. This is the fundamental time period given in the IS code. One should remember always, when the natural period of the building reduce with the increase in the stiffness. If the stiffness will increase, natural time period will reduce, and the natural period of the building increase with increase in its mass. See, if mass irregularity is there, natural period of the building will increase. What is this natural time period and natural fundamental time period? In this natural fundamental time period, we need to natural fundamental time period is given as Tn is equal to 2 pi mk. This Tn is equal to 2 pi under the root m divided by k. Here m is the mass and k is the stiffness of the building. Here, we cannot change the stiffness of the building, but engineers can reduce that mass. How they can reduce that mass? They can choose the simple light weight of materials or light weight of roofs to reduce the mass of the structure. If we will reduce the mass of the structure, then the fundamental time period will be the stiffness will be more, fundamental time period will be more. In the taller buildings, building also, this fundamental time period is more in case of taller building. Now I'll this inverse of this time period 1 by Tn is called as fundamental frequency. Fundamental frequency is called as fundamental frequency, means fundamental frequency is the reciprocal of the time period. If the time period is more, fundamental frequency is less. If the time period is less, the fundamental frequency is more. Every structure is having its own frequency. And what is this frequency? In that frequency, structure resists very less during any oscillation. Structure will not resist the oscillation. Oscillation will be more. Like if you will see that whenever you will walk through the bridge, walk through a cable bridge, then the army person used to say that don't match your steps, because your frequency, your steps frequency will, if the step frequency will match to the frequency of the bridge, then that bridge will rock more, or it can be collapsed. Many incidents has happened in the past that when the frequency of a structure matches with your foot frequency, that structure will collapse. Why? Because at that frequency, structure used to resist very less for the oscillations. In the it happens during the earthquake also. In case of single story buildings, this fundamental period, this fundamental frequency is high. That means if the earthquake is of long period earthquakes, then it damage more in case of single story building as compared to 2-story or a higher story building. I'll show you that how I have tested my building. I have tested my building in single story as well as 2-story building. In that case, I can explain you more that how this fundamental frequency react or impose the damage to the structure. So in case of multi-story building, this fundamental frequency is very high. So if the fundamental frequency is high for the short period earthquake also, that the high story building, if you are having 10-story building, 12-story building, that the building will rock more because of it is having the high fundamental frequency. But we are saying that if we'll match the fundamental frequency with the earthquake forces, earthquake fundamental frequency, but the earthquake forces are used to happen for a very less time, for a fraction of second. Fundamental frequency is there, but so it is very difficult to match that fundamental frequency with the earthquake frequency. But it happened in the past during a particular earthquake that fundamental frequency of the structures matches with that of structural frequency. In case of Nepal earthquake, earthquakes are of long period earthquakes. Those earthquakes are of long period earthquake. That's why in single story building failed. We used to say that if you are having single story building at your premises, it is very strong during earthquakes. Why? Because its fundamental frequency is very high. Fundamental frequency is high. Because of that fundamental frequency, the frequency of earthquake cannot be matched with the single story building. But in case of Nepal earthquake, the earthquakes are of long period earthquake. That's why the more damage has happened in the single story building also. So this is how you can calculate the time period and fundamental frequency of a structure. So here you are having one question here. Question number 9. Question number 9 is there, in which you need to calculate the base shear. You need to estimate the base shear of the building. A three-story masonry school buildings with the following plan is situated in the seismic zone 5. Show the different earthquake resistant measure to be provided with the help of sketches. Give the size and detail of reinforcement. Assume story height 3.3 meter. Door sizes are given, window sizes is given. Also estimate the design base shear for the building as per Indian Standard 1893/2002. Assume the seismic weight equal to 1 ton per meter square. So this is the question number 9. You need to calculate first time period. Now this frame is given in the tutorial. You are having one side is around 20 meters and another side is having 7 meters of length. So you need to calculate the time period in both the direction. and in direction in which the time period is less, we need to take that time period, and accordingly we need to design the structure. Now here we need to design the base shear. The formula of base shear is VB is equal to AH multiplied by W, as you have seen in Indian Standard Code, which is equal to Z by I divided by 2R SA by G into W. What is Z? Z is the, here in Indian Standard Code, Z is the, here it is given, here it is given Z factor. Z is equal to Z, what is called as zone factor. Zone factor Z, that depends upon the in which zone your building is lying. Zone 1, zone 2, zone 3 and zone 4. Zone 5, you can see here in zone 2 there are different kind of intensity: low, moderate, severe and very severe. We have also tested our building in case of for zone 5, considering soft soil condition and under the very severe kind of a loading. Now Z, this is called as 0.36. We used to call it 0.36 G. If we want to test it for the maximum considered earthquake, then we need to induce the forces equivalent to 0.36 G. So we have tested our building for 0.36 G. I'll tell you in the next lecture. And after this is the zone factor, and here another term is there. Another term is I. I is given here. I is the importance factor, depend upon the function use of structure. Importance factor means that how important your structure is. If you are designing your structure as a school building, as a residential building, as a hospital or other kind of a building. So here it is given in table number 6. It is given in table number 6. Here it is given. Here the importance factor, as you can see here, the importance of the services, important services and community buildings with hospitals, schools and another things are given, and that importance factor is given as 1.5. In your question it is already given that the 3-storied masonry school buildings. So school building is given here, so importance factor is 1.5. 1.5. Another thing is R. R is the reduction factor. R is the response reduction factor. What is that factor is, whenever we used to design any building, we used to design for a lower forces, because if we'll design our building for the more forces, the building will not economically viable. But so that's why we used to reduce the forces, and this R factor is applied, because we are not designing earthquake proof building, we are designing the earthquake resistant buildings. That's why we used to reduce that factor, and the IS code has given this reduced factor in table number 7, R factor. So so we need to multiply our base shear with the response reduction factor. That R is given here. Ordinary RCC building, special RCC, moment resistance frames, steel frames. Load bearing masonry walls. Here you can see there in your question it is given as the 3-story masonry building. 3-storied masonry buildings means you are having you will take this reinforced with horizontal RCC band at the corner of the rooms and the jambs of the opening. You can take this factor, R factor here. So you can take this reinforced with horizontal RCC band and vertical bars. You can take this C factor. So the value will be 3. Another thing is this SA by G. SA by G is the average response acceleration coefficient. SA by G is average acceleration response coefficient. It depends upon the type of soil, which on which soil you are making your building. You can see here type of soil, rock or hard soil, medium soil or soft soil. For this, factor is given in this table. Here it is given as SA by G. On for example, you are designing your building for the rock or hard soil. SA by G is given here 1 plus 15t. T is the, what do you mean T? T is the time period which you have calculated. T is equal to, हाँ इसका ये फार्मूला जो दिया हुआ है ना, T is equal to 0.09 h under divided by under root D, which is given in the Indian Standard Code. अभी मैंने जो दिखाया था आपको, which I have shown you here. So you need to calculate TA, TB in each direction. In one direction, the your length is 20 meter. At another direction, your length is 7 meter. So you need to calculate your TA and TB in both the directions. So here, if your TA, TB is in between this kind of a structure, you consider that your structure lies on the hard soil. If you'll consider that your structure is residing in the hard soil, so when you will calculate the T, then you can decide the factor, which factor you need to take. You need to take 1 plus 15t, or you need to take 2.5 or 1 divided by t. This is the factor which SA by G you need to take in your design consideration. And another thing is there. R ये हो गया है. Another thing is there, weight. Weight means mass into MA. Mass into weight is equal to mass into acceleration होता है ना. तो G यानी इसको मल्टीप्लाई करना पड़ेगा. You need to multiply it with G. Z by 2 into I by R, SA by G, multiply by G into beta. Now, you need to consider the damping factor also. Here, a building is having some damping property, where it is given damping. Here in this IS code, damping factor is given. Here it is given damping factor, damping percentage. For masonry structure, we used to consider damping 10%. For masonry structure, 10%. For RCC structure, 5%. And for steel structure, around 2%. So now we are having our masonry structure. So you can consider 10% of damping. So value is 0.09. 8. Okay, this is how you need to calculate. Now it is given seismic mass of the building is 1 ton per meter square. That means seismic mass means 1 story. That 1 story is having the on 1 story you are having the mass of 1 ton. Means 1 ton multiply by 20 multiply by 7. You need to multiply it with area. Your area is, this is your building. Five meter and 8 meters, and here it is 7 meters. So you need to calculate the mass of each story. Now you are having the 3-storied building. On each story you need to 1 multiply by 20 multiply 7. It is around 140 tons. And then you need to multiply it with 3-storied. That means sigma m is equal to 3 multiplied by 140 T. How much load is equal to 420 tons. So you need to design your building for 420 tons. Okay, so we'll do the calculation later on. So here, okay, another question is there. What is the role of stirrups in RCC structure? So stirrups are very important kind of a component in any RCC structure. Stirrups are provided in when you are doing the reinforcement of the columns as well as reinforcement of the beams. Then these stirrups are provided. Why? We are also called it as the shear reinforcement, because of the shear force. The shear force is resisted by this stirrups. What do you mean by stirrups? Stirrups are provided. The function of stirrups is number 1, to keep the main reinforcement in position during any earthquake. These are the stirrups. You have seen the rings. We also used to say it as rings. Whenever you will make any column or any beams, you need to provide the rings in the column like this. If this is the column, so these are the rings. Because during earthquake forces, more forces are concentrated near the joints. Joint region is most vulnerable region during the earthquakes. So we used to, so more shear reinforcement. As I told you, if you are having infill walls in between, it will create more shear force. It will transfer more shear force to the column. So we need to design that this portion of the column for more shear force. So we used to provide closer type of stirrups at the junction region where your beam and column joins. We used to provide the closer stirrups. So this is the shear reinforcement as well as to keep the reinforcement in position. This is why it is this role of stirrups in RCC structure is there. So you need to write it. Then what do you mean by design based earthquake and maximum considered earthquake? I have already told you. Then first question, explain the origin of earthquake, measurement of earthquake magnitude and intensity, ground motion parameters, and earthquake response spectrum. Already explained you, and it is also given in IS code. List of the various failure mode and safety measure for the masonry building subjected to earthquake. This is also given in IS 4326. IS 4326. It is also given here. See, here it is here it is given the building category earthquake resistant features. One category A, category B, category C, category D, and category F depend upon the alpha H. Alpha H. What is alpha H? Alpha H is given. Alpha H is given here in this code. Alpha H is equal to alpha 0 IB. Alpha is design seismic coefficient for the building, and alpha 0 is given in table 2 IS 1893. It is also given to you here. See section 8.4 table 2. Here it is given alpha 0. That depend upon your zone. Zone 5, zone 4, zone 3, zone 2, zone 1. It is an older code in which it is given 0.08 alpha 0. Basic horizontal seismic coefficient. So it is given here. Here you need to decide which type of your building. Suppose your building is residing in E type, A type, B type, C type. Here in question number 9, you need to consider the building category E type. Just write down. In question number 9, you need to consider your building E type. For that building, you need to design the openings also. How much openings need to be there? How much vertical reinforcement? As I told you that some vertical reinforcement need to be provided. Some horizontal band need to be provided. But how much diameter, how much dimension of your bars should be there? So it need to be calculated through code. So here it is given. In figure number 6, it is given height of the door, B1, B5, B2, all the things are given, and you need to calculate from here. Table number 4, size and position of opening in load bearing walls. D type and E type building, distance B5. Here all the things are written. Only you need to design your building according to your question. You need to consider B type building, cement sand ratio, positioning of the walls, everything you need to calculate. Here it is given completely. Strengthening arrangement of recommended for masonry building. For E type 1 to 3, A to H. Strengthening need to be provided all story A to H. Means here you are considering E type building. A to H provisions means here A, mass mortar, lintel band, roof band, vertical steel bars at the gem of the opening, bracing in the plan at tile level of the roofs, plinth band where necessary, dowel bars. So these all you need to be provided. Understood? So you need to see the codes and you need to provide the accordingly. So here it is also given in 4326. All the arrangements, how you need to provide lintel band, roof band. Here it is given recommendation longitudinal steel reinforcement, concrete band. Now your building category is E, number of bars.
सर एक डेटा नहीं दिया हुआ है.
कौन सा?
B5 बताया ना कि ओपनिंग फ्रॉम द कॉर्नर, डिस्टेंस ऑफ ओपनिंग फ्रॉम द कॉर्नर B5. तो that was not given in the question.
B5.
Yes.
Distance from the opening.
Distance of opening from the corner.
Distance from the opening from the corner should not be less than 600 mm. As I told you in the earlier lecture also, it should not be less than 600 mm. So the data which are not given, you need to consider. The distance from the corner should not be less than 600 mm. That is Codal provision.
Okay, thank you, sir.
Now here it is written table number 6, recommended longitudinal steel reinforcement. Longitudinal steel reinforcement, here you know all the things are given, steel bands and how you need to provide the steel reinforcement in the column and beam for horizontal bands, horizontal and vertical bands. Don't worry, I'll do it with you also. So from here you need to design your building. Vertical steel reinforcement masonry walls given in table number 7 with rectangular masonry units. Here for E category, top bottom, top middle bottom, top third second bottom, top third second and bottom. So it is not necessary that you need to provide only 2 bars, as your building reside in zone 5 and need to be resist more lateral forces. So sometime you need to provide 4 bars also in case of horizontal bands. So depend upon the design of the masonry building. So here all the design is given. So I think everything is clear. Here one question is given, question number 5, explain the brittle and ductile mode of failure in reinforced concrete component. So brittle mode of behavior, if the RCC component fail in shear, axial tension, axial compression, then that mode of failure is brittle kind of failure. In shear, always brittle kind of failure is there. We always observe if your this stirrups are not provided at a regular intervals, so brittle kind of failure will be there. Axial tension and axial compression. So these are the brittle mode of failure. Ductile mode of failure under flexure. How we can achieve that? We used to design the, we are keeping a link, a weak link in our buildings. In my next lecture, I'll show you how I have designed my building smartly. I have given a weak link into my building. So that weak link will be ruptured and my building will not be damaged. I have designed intentionally that weak link. That weak link is not a structural member. That weak, whenever my building will rock in the earthquake, that all the stresses will be taken by that weak link, and that weak link will be ruptured, or that weak link will be yielded without damaging the structure. So that is called as the strength, the ductile mode of behavior of the structure. That's why here we are keeping the stirrups closer to the joints, so that whenever the more forces are concentrated near the joints, it will behave as a ductile kind of a behavior will be there in that case. So this is how you can answer that question. What is the effect of infill on the seismic behavior of the frame building? I have already explained you. It creates more additional shear force to the column. Additional shear force to the column, as well as additional bending moment to the column. So that we need to design for additional shear force and bending moment, already given in IS code. As I have told you that this infill effect of infill walls, how it in case of soft story, you can explain by taking the example of soft story also. So here I have explained you all the questions. So now you will do the tutorials in the next after the lunch. You will do the tutorial after this short break of tea. Just half an hour break for tea. Now we are breaking for tea. So after half an hour we'll meet again, and in that lecture I'll tell you how I have developed one new technology by keeping all the parameters in mind. Weak link, ductile behavior. I have improved the behavior of the structures by improving the elastic behavior of the building. I designed my building in such a way that building remain in elastic state. It will come back to its original position. After the test, we have observed that after attaining a 10 centimeter of deflection, it came back to its original position. Okay. Now, somebody was telling that what are the futuristic plans for earthquake resistant design. So here I'll explain you how, what we did. We did some research, and we have made one interlinked block masonry system with viscoelastic energy dissipator links. We have developed this new technology, completely new technology for load bearing type of a structure. But still the research is on. We are also testing this technology for the framed structure also. As I have already told you that infill used to have more pressure on the columns, additional shear force on the column. So we need to design the columns for the additional shear force in case of earthquakes. So we are testing that this technology, because in load bearing structure the elastic range of the structure is too much. After attaining the deflection of 10 centimeter, the structure came back to its original position. So we are thinking that in framed structure also, in case of infills, it will create much less pressure on the column. So if it will create less pressure on the column, it will transfer less shear force to the column. So we need to design the column accordingly. And if our test will be successful, then we'll again test it for the full scale 3D model. Now we are testing it in the 2D model. So in maybe next week or in the month of June, we are going to test that technology in IIT Roorkee. So I'll explain you that what is this interlinked block masonry system and how we have developed this technology. So this is the research part. When I took up the research, under the guidance of Dr. Pankaj Agarwal, professor in IIT in the Department of Earthquake Engineering, IIT Roorkee. So we thought that we should, there are a lot of problems in case of masonry structures, in case of load-bearing masonry structures, because in masonry structures the main problem is of joints. In any brick construction or in any block construction, you need to join blocks with cement mortar, or some interlocked kind of block masonry system has also been developed and patented by many researchers. But if you read that some of the limitations which are prevailing with those kind of interlocked block as well as masonry structures, in case of masonry, brick masonry or simple block masonry structures, researchers has told that unless and until it is coupled with the reinforcement, unless and until you are providing the vertical or horizontal reinforcement into it, so you cannot make your structure in case of seismic prone areas. So it will behave very poor in case of seismic prone areas, because in as I told you that in earthquake forces, if we want to, this is the concept of energy. Lot of energy, huge amount of energy is released during that earthquake, and if you want to release that energy, the only concept is energy dissipation. You need to dissipate that energy, or you need to absorb that energy. So for that purpose, we allow some of the damage into the building, and at the same time we need to provide a particular stiffness to the building, so that under moderate kind of earthquake, no crack should be developed in the building, and your building should remain intact. In case of moderate earthquake, your this damage should happen only in case of the severe earthquakes or a comparatively less severe earthquake. But in case of very moderate earthquake, the crack should not be there. So we kept that technology into the mind, and we have studied different kind of dampers which the researchers are providing in case of multi-storied building. There are many research, there are many dampers which have been developed by the many researchers, and they are providing it into the building in case in the form of bracings or in the form of base isolation technology. But that technology is very, very costly. We cannot adopt that technology in case of load bearing type of structure. The load bearing type of structure, the structures, those structures a common man used to make their homes. If a common man used to make their homes, we are having different different Indian standard codes, and we are having different code of practices. Like I have also given you IS 1893 4320 and another codes for masonry as well as low strength housing. But still we are making our structure vulnerable to the earthquakes. We are not providing any earthquake features in our structures. Why? Because our masons are not trained. Our masons are not trained, and there is a lack of awareness among the people that how they can make their buildings earthquake safe by providing certain kind of a norm. So we thought of that, why not we should provide a simple solution for the earthquake earthquake resistant structures. If we will not provide any vertical reinforcement, if we will not provide any bands, then can we make our buildings earthquake safe? So we have studied many things. Despite here, I will take the example of Nepal. In 2015, Nepal earthquake was there. So we have studied that different pattern of the waves in the Nepal earthquake. So we saw that in Nepal earthquake, those earthquakes are of longer period. And as I have already told you, in longer period earthquake, most damage will occur in single story building also, because the fundamental frequency of a single story building is very high, and in case of multi-story building, fundamental frequency of the structure is less, and during the large period earthquake, sometimes fundamental frequency of structure in which the structure is not offering any resistance to the oscillation, which is offering very less resistance to the oscillation. That means at that frequency, the structure can oscillate much more as compared to the other frequencies. So we have studied different patterns. In that Nepal earthquake, around 5 million buildings were damaged, and approximately all the buildings are load-bearing type of buildings, and around 8,660 people were died, and around 22,000 people were injured during the during the main shocks. And after that, Nepal earthquake has experienced many aftershocks also, and there are many damage which are reported by many of the researchers, and many research have been done on the Nepal earthquake. So we have also studied the parameters and patterns of this Nepal earthquake, and we have compared our result with the parameters which have been induced by the earthquake. So this is how, not only Nepal earthquake, we have also compared our results with other earthquakes, other major earthquakes which have been hit in the world. So we have compared our results. So we got the very encouraging results in case of that. In case of this developed technology, the developed technology is we have applied the patent, and we got the provisional patent number also for the technology. The technology have been presented at various international as well as national levels, and got many awards. So now I'll explain in this technology. Now the question arises that though we are having that much of code of practices, that we are having that much of knowledge, we are having many civil engineers, but still we are not making our buildings earthquake safe. As I am running this program on earthquake risk management for rural and urban housing, but still the civil engineers are not having the knowledge of seismic forces and how those seismic forces act on the structures, and how you need to read the Indian standard codes. If you will do the tutorials after the lunch period, you will see that with a small provision, with a small intervention of IS codes, you can your building can withstand the earthquake forces. Here, you know, if I'll say that you can enjoy earthquake by sitting in your home, this will be your reaction, that can we enjoy earthquake by sitting in your home? So what I am saying, it is not possible. But we have tried it, that after a strong shaking, we have tested our structure with a great shaking testing, and it proves that after having a very small damage, negligible damage, the structure withstand at its original position. The structure came back to its original position. So we have increased the elastic property of the structure. So here, what we have used the old and used radial rubber tires for developing the viscoelastic link elements. Why we have used this old and used rubber tires? When we started our research, I was searching for the material, that what material I can use for this, for making my low cost viscoelastic link elements. So earlier I was thinking that some titanium kind of a material I should use, but that titanium is very costly material, because some shape memory alloys, if you have heard the name, for the person who need to do the research, this is also a very much research area, that you should research for the masonry structure. Shape memory alloys. Shape memory alloys are the alloys which return back to its original position when their temperature will increase. As the temperature will increase, it will come back to its original position. So if you'll search Google, then you will find many papers for the shape memory alloys. So that kind of material I thought of. Then I thought that I should use this neoprene rubber also. So neoprene rubber, when I searched for the neoprene rubber, then the neoprene rubber is a very costly affair. It is around 2,000 to 3,000 rupees a kg. But as I went deep into the research, then I found that this neoprene rubber are available in different quality as well as different material. So cost of the material varies from 170 rupees to 3,000 rupees. So there is large variation of the material. Then one day, me and my guide we were traveling by his car, my guide's car. So the tire of that car got busted. So when we were changing the stepney stepney of the car, so we saw that busted car tires, it is having some steel wires. So we thought of why not we use this material. So when I studied this the behavior of this radial rubber tires, you must have agreed that this rubber tire life of the rubber tire is very less. If your vehicle will stand for 10 days or 20 days, 10 years, or maybe 5 years, so you cannot use your car because your car tire will be degraded. So in that case, it was very difficult to use the rubber of radial rubber tire. But as I have studied, I have talked to the manufacturer of this radial rubber tire. So as I read that how this tire has made, then I got the answer that there are many type of tires, and there are basically I categorized in two kind of a category. One is tires for your passenger cars, and one tires for your load carrying vehicles like trucks and other vehicles, and your passenger car. In load carrying vehicles, the tires are made up of different kind of a material like natural rubber, and and having different components of the tire. First component of the tire, the basic most earlier the tire problem, as we have studied that this tire problem is not the problem creating part. In India we are having lot of rubber tires having if you will visit this Meerut near the Roorkee, so you will find that the whole kabadi market for the rubber tires only. There are huge mountains of rubber tires. You will see that it is so scaring that much of rubber tires available. And what they are doing is, and only in that region they are doing that, they are removing the upper rubber part of the tire and they are sending it for the recycling. But some part of the rubber tire cannot be recycled, and they are sending that part of rubber tire for making the for burning in brick kilns. Mostly they are sending it for burning of brick kilns. Earlier I have inquired, I have talked with them, so that earlier what you were doing with this material. So they told us that earlier we are having the belts, we are running our wheat mills as well as some of the equipments. There are some belt kind of arrangement on which those machines used to work. But nowadays, due to modernization, due to research, so we have get rid of those belts. So those belts now we are not selling this material for making the belts. So now we are selling this material at a very cheap cost for burning in the brick kilns. So further we have studied, and we saw that this is the great problem worldwide. This used rubber tire is a great problem, and the biggest graveyard of this rubber tires lies in Kuwait. Even you can see that this graveyard can be seen from the space also. You can see the space photograph here. It can be seen from the space. That much rubber tire is available. Now what is the problem with this kind of a dump yard of rubber tire? Because of huge summers when the temperatures reaches above 50 degrees Celsius in case of Kuwait. So burning of tire will be there, and huge amount of carbon dioxide gas used to be released during that point of time when this tire catches fire during the summers. So it is a greatest problem, because day by day as the urbanization taking place in the world, we are having lot of cars on the roads. Earlier we used to have only 1 to 2 cars, but nowadays a single family used to have 2 to 3 cars. So the tire, we are changing tires from for every 20,000 kilometers or 30,000 kilometers, we are changing our car tires. So in this case, this is the picture of this ply of this components of radial rubber tires. So radial rubber tires are having different components. First casing ply first casing ply is there, then one belt of steel wires embedded diagonally into it. Steel wires are there. There are 2 layers of steel wires that are embedded diagonally into it. After that, two meshes of nylon fibers. Some fibers are there. That 2 layers of fibers are also there above that 2 layers of steel wires. So after that, the tire is mounted. After that, rubber tire is mounted on this, because you know the rubber tire used to experience lot of heat and as well as air pressure. If your vehicle will run, lot of heat will be produced, and that heat will be resisted by your rubber tire. So base of that rubber tire is so strong that when we talked about the car, this tire manufacturer, they told us that if we will keep this lower part of that tire at 100 degrees Celsius for 1 week, the physical and chemical properties of this material doesn't change at all. So this is the testing of the radial rubber tire. Again, we have checked many documents also for confirming the performance of this part of the radial rubber tire. So what we did, we took the passenger car tires. Now there are 2 types of car tires. One is load carrying vehicles. Now load carrying vehicles, replacement of tire is very frequent. Why? If one load carrying truck, they are moving continuously. Because your your passenger cars, you are taking your cars for a certain distance, you are coming back from your office, you are taking your car somewhere else. But in case of load carrying vehicles, in case of trucks, your trucks are moving continuously, and the changing of that tire is very frequent. So that tire is made up of natural rubber, and the life of the tire is also very less. So because because it is very frequent to change that tire. But in case of passenger car tires, the base part of that rubber tire is made up of styrene butadiene rubber. The particular type of rubber name is styrene butadiene rubber. The styrene butadiene rubber is made up of made by crystallization technique. So this is the rubber which is having prolonged life. If the chemical properties are not changing at 100 degree Celsius temperature, by keeping it for a 1 week at a constant temperature, that means the life of that material is very high. So we have decided that now we will take this material and we will make our viscoelastic links by taking this material. But we are not sure that whether the material will work or not. In another picture, you will see that when we thought of that we will use the base part of this rubber tire, we are not knowing that from where we will get this base part. But as soon as I visited this Kabadi market in case of mirror, then I saw there that this availability of material is no problem. We are having plenty of material and is available at a very, very cheap cost. So in very cheap cost, as well as it is a environmental problem. The disposal of that kind of particular material is also a problem of disposal, because upper part of the rubber we are sending it into the recycling, but the lower part of the rubber we are not sending it in the recycling. It cannot be recycled because recycling cost is more as compared to the recoverable material. So this proves to be very cheap fuel for the kiln market. So because it used to burn for a longer time, and available at a very cheap cost, because if you'll burn wood or some component, that it costs much more as compared to this. So this is why we have used this material. Now we have converted in this research. This is the one part of the research that we need to make the viscoelastic link. But one thing I told you, that building should have the initial stiffness to resist the small earthquake loading. Now, if you'll see this material, if you'll see the base part of the rubber tire, it is a very flexible kind of a material. If I'll use it, it cannot resist any initial, it is not having any initial stiffness. It is not having stiffness. It is a very flexible material. if I'll use it as it is, then how I'll use it in case of buildings? It will fail. It will not serve any purpose. So first problem, we need to provide a initial stiffness to the material. This is one. But in this research, there are two components. One, we have developed the one interlinked concrete blocks, and second, we have developed this viscoelastic energy dissipator links. So here we have developed the strong concrete block as well as weak viscoelastic interlinking element. We thought when the earthquake force will come, we will provide the initial rigidity to the material. In small earthquake shaking, nothing will happen to the building. But in case of large shaking, in case of if earthquake magnitude will cross 7.5 or 8, will cross the so what will happen to the structure? So in that case, these viscoelastic links will rupture, and without damaging the concrete blocks, and it will take all the energy, it will absorb all the energy, it will behave like a shock absorbers. So this is the initial thinking in our mind, but we were not clear whether this technology will work in the structures or not. So research is just you need to give hit and trial methods so that your technology can be succeeded. So these are the interlinking concrete block elements. Now recall all the earthquake measures which I have told you in lecture 1, lecture 2, lecture 3. In that case, what is there in masonry construction? Bricks, joints, corners. What are the why? I told you that in the earthquake, corners will fall, corners will split. In case of stone masonry, your stone will split. You need to provide a through stone. So keeping all the things in mind, we have developed these concrete blocks. We have developed 3 types of concrete blocks, and these concrete blocks have been developed by keeping in mind that it should be adopted by the local people. Because we are making this technology for the local people, and it should be of very cheap cost. So this, we have done 3 types of concrete block. One is stretcher block. This is the stretcher block. This is the half block. What is the half block? Just half the stretcher block, but just doing the half of stretcher block. This half block has been prepared, and after that we have prepared this corner block. This corner block is little bit bigger in size. It will work as a through stone for the corners. That's why we have developed this corner block, because we should not that the corner should not split. So we have developed this corner block. Corner block size is little bit bigger than that of stretcher block. So now we have developed this concrete blocks by M20 grade of concrete, by keeping the mix 1:1.5:3. Okay, so this is the M20 grade of concrete, and for developing this blocks, we have developed the molds, block molds, having these grooves. And the beautiful part in this technology, we have not used any cement mortar for joining these concrete block with one another. Abhi, what we used to do, we are keeping one brick, then we are applying mortar, then keeping another brick, and above those layer we are again spreading the mortar, then again we are using a lot of cement to joining the one brick and another. This stretcher block replaces 6 brick by volume. One stretcher block replaces 6 bricks by volume. That means if you will keep one block, 6 bricks have already been replaced, and the height of the block, height of this block is around 150 mm, around half a feet. Suppose you have kept one block, half feet height is over. Another block, 1 feet height. So the construction is very fast, and you need not to apply any mortar in between the joint. Just we have joined this concrete block by dropping the viscoelastic link elements. That's it. Now, how we have developed this viscoelastic link elements for providing initial rigidity. For providing initial rigidity, we have provided a very thin steel plates, available in the local market of 0.4 mm. 0.4 to 0.45 mm steel plates are available in the market. We have cut these steel plates, and we have provided these steel plates at each of the face of this viscoelastic links. Now, what the depth of this material, depth of the ply of that material, that the base part of the radial rubber tire is known as ply. Radial rubber tire is having thickness of 6 to 7 mm. It varies because it is a scrap kind of a material. So when a person used to peel the rubber above that tire, so sometimes it is 6 mm, sometimes it is 7 mm. So 6 to 7 mm the thickness of this radial rubber tire. And we have in this as you have seen this concrete blocks, we have designed the grooves. We have designed the groove in such a way that the groove size should not be more than 5% of the total mass of the of that block, because if it will exceed that limit, the strength of the concrete blocks will be less, and in earthquake force, this viscoelastic link will break our concrete block, and we don't want that our concrete block should be disturbed, or our concrete block should be damaged. So that's why we have we designed this grooves of the in the concrete block very smartly. We have developed two type of viscoelastic links. One is vertical and one is horizontal. Here two type of interlinking link elements are there. One is vertical and another is horizontal. In vertical, vertical links in this concrete blocks, if you'll see, vertical links will resist translation. When translation force will be there, then it is resisted by the translation, or translation forces will be resisted by the vertical links. For joining one block with another, there are 6 vertical links are there. 6 vertical links, and horizontal links are provided to resist rotational moment, because in earthquake forces there are translation as well as rotational moment occur during the earthquake. So for the rotational moment, we have developed this horizontal links, and for the translation, we have developed this vertical links. So there are two type of links have been developed. These are the pictures of vertical as well as horizontal links. So this is the very simple technology, and by this technology, we have developed full scale 9 models. We have extensively tested that models under shake table and shock table, as well as under cyclic kind of a loading. And in this now I am showing a small film for this technology, so that you can have the feel of the technology, how it has been made, and how it can be made in the local community, in the local vicinity. And this technology is specially made for the hilly areas, because where the cost of the brick is very high. Cost of the brick is very high, as well as the labor cost is high. So we are saving the cost of that brick and the cost of the labor. The cost of the brick in the lab we have developed depend upon the cost of the material at a particular place. But in Roorkee, we have developed this block cost around 20 to 25, 24, 25 rupees, like that. But replacing 6 bricks cost, if 1 brick costs 6 rupees, then cost of the brick 6 brick is 36 plus mortar plus cement, all the things plus sand. So we have reduced the cost of construction here, and this is very innovative approach, and we called it as interlinked concrete block masonry system integrated with viscoelastic energy dissipator links. So this is the very innovative technology. Now if you will see the film, and you will, during the test in the single story building, when we have tested the single story building, then we saw that the upliftment of roof was there. The upliftment of roof was there, but in this case, when the lateral force is applied to the building undergoes the shear kind of a forces. The wall undergoes shear kind of forces in case of in plane as well as out of plane kind of action. In out of plane, or overturning of the walls will be there. But in case, because of this viscoelastic link, we have tested these links individually also. Individually, when we have tested these links, so we saw that after displacing a particular displacement, after having the particular displacement, these links come back to its original position because of this steel wires embedded diagonally into the material. That wires provides stiff toughness to the material, as well as that small rubber part which is available in the ply, that provides flexibility to the material. Now we have provided flexibility as well as stiffness by providing these steel plates. So this is how we have developed the technology. Now I am showing a small video films. After that, I'll show the results. What are the results? How the earthquake forces travel during the testing, during the structural testing, and how we have compared that results from one to another earthquake. How this fundamental frequency behaves in a different manner. So I'll explain you that. First, I'll show you small video film. So this is the future. We have developed this technology for the future work.
One of the most dangerous and destructive form of natural hazards. Each earthquake not only brings with itself devastation, trauma, and fear, but also brings in several challenges for the researchers. Though over the years, researchers and scientists have tried to predict earthquakes, yet the 100% precise prediction is still not possible. As a result, thousands of people lose their lives during earthquakes due to collapse of man-made constructions. Masonry is one of the most affordable and adaptable building material in the developing countries. In India itself, which is the second largest developing country, most of the population lives in masonry houses. As per the census report, 84 million houses in India are made up of burnt bricks, and around 62 million houses are made up of mud or unburnt bricks. Although masonry is the most used building material, still the seismic performance of masonry construction is not satisfactory. Worldwide, many researchers have churned their minds to improve the performance of masonry structures, especially during earthquakes. One such research is being carried out at IIT Roorkee's Department of Earthquake Engineering, where a new, affordable integrated system of viscoelastic links made up of used and old rubber tires with interlinked block masonry system has been developed.
At Earthquake Engineering Department, IIT Roorkee, we are working on use of conventional as well as non-conventional materials for construction, and we have here testing facilities where we can test the material for its application in earthquake-resistant construction. And in this direction, one of the established system which we have developed recently, where used tires are used to dissipate energy between concrete blocks, and this material can be used as an efficient alternative to our conventional materials. And this is not only earthquake safe, it is also reducing the impact of construction activity on the environment.
The developed system is not only eco-friendly, but can also withstand extreme earthquake conditions like those of severe seismic zone 5.
As you are aware, India is a seismic-prone country, and the whole country is divided into the 4 zones, starting from the zone 2 to zone 5. Zone 2 is the lowest seismic zone, and zone 5 is the highest seismic zone.
As a part of the research, well-designed slotted concrete blocks and viscoelastic energy dissipator links made up of used radial rubber tires encapsulated between very thin steel plates have been developed.
interlinked block masonry system with viscoelastic link is a technology in which two parts are there. One is viscoelastic energy dissipator link, and second is interlinking block. This interlinking block is joined by using this viscoelastic link, which are developed by using used and old rubber tires. And why we have used this old and used rubber tires? We have used the ply of the used rubber tire. These ply of the used rubber tires having steel wires embedded diagonally into it and having the property of viscoelasticity as well as steel wires provide strength to the material. So we have used both the property of the material and we have converted this waste material into a useful material.
The reasons behind using worn-out radial tires are manifold. Primarily, radial tires are made up of a copolymer of styrene butadiene rubber, which is a viscoelastic material. Secondly, the base part of radial tire, known as ply, has mostly steel wires embedded diagonally in the rubber, which enhances stability, strength, and viscoelastic property of the material. Thirdly, they are available at a very cheap cost in the kabadi market. Along with all this, high strength, high tear resistance, high shear resistance, and high toughness are the properties because of which used radial rubber tires were considered most effective for the development of viscoelastic energy dissipator links. But the most important reason is that used radial rubber tires cannot be recycled easily, and even if they are, they emit out gases which are very harmful to the environment. Basically, disposal of a byproduct like used rubber tires is not only a great problem in India, but worldwide. The biggest graveyard of tires lies in Kuwait and can be seen even from space. Sometimes these old and used rubber tires are used as a fuel for burning, especially in brick kilns, as they prove to be very cheap fuel, but at the same time release dangerous amount of pollutants into the environment. Similarly, the reasons behind using concrete blocks in place of traditional burnt bricks are also manifold. Actually, for the making of traditional bricks, a large area of fertile land is dug up and molded into the shape of bricks, which are then heated at a high temperature in kilns or bhattas. During this whole process, not only is the topmost fertile layer lost, but also the heating process gives out huge amounts of smoke into the air, which is loaded with pollutants. Thus, by replacing the need of burnt bricks with concrete blocks, the idea is to preserve the environment in more than one ways. So, in the developed technology, three types of interlinked concrete blocks, that is, stretcher block, corner block, and half block, have been developed to make the possible arrangements, that is, L, T, or cross in the masonry construction. Interlinking of the blocks has been done with the help of two types of viscoelastic links, one vertical and one horizontal. No cement is used for the interlocking. 4 vertical grooves have been provided to restrict translation and 2 horizontal grooves to restrict rotation under severe earthquake loading. The strength of the concrete blocks was kept much higher than the viscoelastic links through the yielding of low-strength viscoelastic links and friction between the concrete blocks. The developed technology was then tested under severe conditions on shake table and shock table test facility by simulating artificial earthquake excitations.
This is the shake table facility. On this platform, we can actually simulate earthquakes like they happen in real ground. This platform on which I am standing can be moved in one vertical plane, exact plane, with the help of 3 hydraulic actuators. One you can see horizontal right there, and 2 vertical actuators. With the help of these 3 actuators, this entire platform can be moved in one vertical plane, horizontal and vertical. And that helps us to study the simultaneous effect of horizontal as well as vertical earthquake ground motion on the specimen, model specimen that we can mount on this top of this platform. and study its behavior during earthquake, how it would perform during an earthquake.
Its seismic performance was analyzed experimentally also. A full-scale housing model with maximum load carrying capacity was made on the shake table and tested under a series of simulated earthquake motions. Peak ground acceleration of 0.18 G and 0.36 G, that is, design basis earthquake and maximum considered earthquake of zone 5 respectively, considering soft soil condition, was applied. The experiment was a success. The energy imparted was completely dissipated through friction and viscous damping of viscoelastic links. The model retained its original shape and position after the tests. Further, by increasing the severity, single-storied and two-storied models were also tested on shock table by giving impact type of loading. 3 consecutive shocks of increasing intensity were applied. Test results showed no distress or damage to the model. The elastic plastic behavior of the links revealed that the model regains its original position after completely dissipating the energy imparted during the shock test.
For the practical implementation of this technology, a 2-story full-scale model was prepared on the shock table, and the model is again tested under a series of a severe shock, and it was found that the most of the energy has dissipated at the bottom part of the model, and the top story of the model is remained intact.
Besides better earthquake resistance capacity, there are several other advantages of interlinked block masonry system over the conventional masonry system. It is more rational and simple, supports speedy construction work, and has high energy dissipation capacity. Moreover, it leads to clean construction at the site, since the blocks may be cast either in factory or at the site by using different types of locally available materials. For future translation of this research into large-scale use, well-slotted concrete blocks and viscoelastic links can be readily made available in the market.
One of the challenges in any engineering development is converting challenges to opportunities. In this technology also, we are converting a big challenge, which is disposal of the waste material, that is rubber tires in this case, to the advantage. That is using those for dissipating energy during earthquake and making our buildings safe during earthquake. So this not only saves the problem of disposing of used rubber tires, it is also helpful in saving lives during earthquake. And that's how we convert the challenges to opportunities.
So this is how we have tested this technology. We have tested extensively 9 full-scale models have been tested, to have the complete investigation that whether we can use it in this technology into the field or not. Now, we have demonstrated this technology in Make in India at Bombay, and many builders came to us, and they want to adopt. Many local people also came to us, and they adopted. They want to adopt the technology. Now, as we have applied the provisional patent for the technology, so now, if as soon as we'll get the patent for the technology, so the local people can use this technology. That technology will be available in the market. So. How we can use this technology only when we can get this interlinked block into the market. As you go to the market in bhattas and all these things, you can the bricks are available at bricks are available easily. But in case of these concrete blocks, if the technology pick up at especially in hilly areas, these concrete blocks will also be available easily in the market. And the further this this interlinking viscoelastic link element. It is the cost of this linking element is very cheap, because one element cost less than 25 paisa or so. So because this steel plate is also of very cheap cost, because of it is very light in weight. So if you are applying any earthquake features, like you are having vertical reinforcement, you are having horizontal reinforcement, you are providing more cement mortar to the material, you are adding the mass to the building. Here the weight of the one stretcher block we have kept around 20 to 21 kg, which is nearly equal if you'll join 6 blocks by volume. So that lump of bricks will weight similar to 20 to 21 kg, or maybe 19, or the weight of the concrete blocks as well as the 6 bricks is nearly approximately same. So we are not increasing the mass of the building, but at the same time, without providing any vertical and horizontal reinforcement, we are dissipating the large amount of energy during the earthquake motions. As told in the picture also, we have tested this technology in design based earthquake as well as maximum considered earthquake. So here you can see that when you will see the graphs here, this is the graphs of design based earthquake. So in case of design based earthquake, the energy is not dissipated much, because of this initial rigidity. We have provided initial rigidity to the material. When the small shaking is there, the structure behave in a elastic manner, and no cracks, nothing is there, no damage is have been absorbed during this design based earthquake. But when the earthquake shakes more during the maximum considered earthquake, that means 0.36 G, as you have seen this code Z factor. If you will see the Z factor, zone 5, the maximum sphere factor is 0.36 G. So we have tested that structure. Now you can see that during these graphs, the energy is dissipated largely, and it is not transferred from base to roof. In conventional cases, if you are residing at an upper floor, your building will shake more at the upper floor as compared to lower floor. But in this case, your lower building is shaking, but it is not affecting your upper floor. We have also tested the 2-storied building, as you have seen in the test also. In the 2-storied building, we have kept table, chair, even vase in the upper story, and we have observed during the test, after having the huge impact type of a loading, the furniture didn't move even a single mm on the first floor. So that means energy is not transferring from ground to the second floor. If we'll go higher than second floor, third floor, fourth floor, we are recommending this technology up to fourth story only, because it is a load bearing type of a structure. As we go up and up, the performance of the building will improve drastically, because we are providing weight to the building, and this viscoelastic links will behave in a very well manner, because we have designed this links to behave under shear as well as bending. So when it will come in, the forces will come this viscoelastic link behave shears as well as bending, they will behave very well. In first case, you have seen the upliftment of roof was there. That's why we have made the 2-story building, that we want to see that if the weight of the load of the building will increase, that what will be the effect on the technology. So here you can see that we have calculated the fundamental frequency and damping for the structure. Here you can see the transfer in transverse direction, longitudinal direction. We have calculated the fundamental frequencies both the direction. You can see here the fundamental frequency is 9.37 and around 6.25 in 9.37 in transverse direction as well as 6.25 in other direction. Now we have calculated the transfer function, how that the force have been transferred during the this earthquake kind of a motion. So then we have calculated this. Here you can see that this graph is from base to sill level, means base to the lower part of your window. You can see that there are no much difference between the graph. Your graph is almost a straight line. So up to sill level, there is not much much variation. But as you go from base to upper story, top story, then you can see here the fundamental frequency. I told you, at a fundamental frequency of a structure, the structure will move, will oscillate, will move more during earthquakes. But here you can see that when the fundamental frequency was 9, the transfer function, the earthquake forces reduce more than 50%. This is the percentage. So more than 50%. This is the force. Force was increased up to 300%. But here it reduced to 50% at its reach to its fundamental frequencies. So drastically reduction in the earthquake forces. So here we have dissipated all the energy and at a very cheap cost. So this is how we have developed this technology. And during the test, during MC level, we have seen that only small openings was there, because we have not provided any mortar in between, anything. We have not provided any mortar in between. Small opening of at somewhere less than 1 centimeter or 1 centimeter was there, but no structural damage. Nothing is there. Roof was intact at all. No structural damage have been appeared in that.
Plastering is very difficult in this system.
No, plastering, plastering is just similar to as you are doing plaster to your normal structure. Plastering, when you are joining the bricks, with one another, then after that what you are doing, you are preparing the plaster 1:4 mix, and you are applying that plaster. That is how this is a normal building.
Blocks are shaking during
Block they're shaking during that earthquake, but during that earthquake your normal brick structure is also shaking. In that case also your plaster will crack. But I told you that we have provided a adequate stiffness during a small earthquake, like magnitude 5 or so. Your structure will not shake at all, and because of this initial rigidity, nothing will happen to your structure. But when it will shake with a maximum considered earthquake with a magnitude more than 8 or 7.5, more than 7.5, then only your plaster will crack, only your plaster will come out. Then how does it matter if plaster will come out and you are enjoying earthquake by sitting in your home? How does it matter? Nothing. You are safe. You are safe in that building. And though you have not provided any earthquake features, not provided any vertical steels, any horizontal steels, any bands. We have not provided any bands. We have only joined our structure with the viscoelastic links. That's it. So this is all about which we have developed the technology. These are some of the advantages. In film also, it is already told that it is a very robust kind of a technology. You can construct it at a very fast rate, and as how does the cost of the construction reduced? You have reduced the cost of the brick, cost of the block, as well as you are not using any mortar. Only plastering has been done after your construction. And another thing, you are not providing any vertical and horizontal reinforcement, so reinforcement cost curtailed. Then your workmanship cost, your labor cost, it also reduces.
Sir, one question.